Welcome back to the formulaic approach. Now in this video, we are going to talk about the concept of aromaticity. So the word aromatic was long used for benzene derivatives alone, which was first used for substances that were extracted from plants that had sweet-smelling oils. So it was later on that scientists decided to use them for certain structures, okay, that has the following properties. So a structure is aromatic if it is cyclic first. It is cyclic molecule. The second is that if it is fully planar. What does fully planar mean? It is sp2 hybridized. I'm going to explain all this later soon. Now, fully planar and fully conjugated. Okay, fully conjugated. What does fully conjugated mean? It means it has alternating single and double bonds. Then the third condition is that it must follow Huckel's rule. Now, molecules are either classified as aromatic, non-aromatic, or anti-aromatic. Okay, so for example, when I draw some structures now, I'm going to be asking us whether they are aromatic or not. So now let me explain what cyclic molecule is. A cyclic molecule, obviously, when you hear of aromaticity, the first molecule that comes to your mind is benzene, okay? Benzene. So I'm going to be using benzene ring as an example. So let's draw one of the canonical structures. So you already know that this actually does not exist in reality. What actually exists in reality is the resonance hybrid. This is this way we draw it. So this and these are canonical structures of benzene. What I am saying is canonical structures of benzene. So, and each of these separately do not exist in reality. So, what exists in reality is somewhere in between them, okay? So, this is also, so this way we draw them so that you know that their resonance occur among them. So, because of that, what we use is this is the resonance hybrid that occurs, that actually happens. What this cycle that you see in the middle is showing is that the pi bonds are fully delocalized. So fully planar, fully conjugated, that is with fully delocalized pi electrons. Now, the thing is this, that if the electrons are not fully delocalized, that is, if they are not fully spread around around the molecule, then the molecule is not aromatic. Is that clear? So like I was saying, I said this is the resonance hybrid that actually exists in reality. Okay, the resonance hybrid that exists in reality. Now, why did I choose benzene as my example? Benzene is my example because it's the most important or the most famous, the most popular aromatic hydrocarbon. So now let's use benzene, for example, to judge aromaticity. We have the first condition being cyclic. Is benzene cyclic? Of course. When is the molecule cyclic? The molecule is cyclic when the first carbon links to the last carbon with the last carbon. So for example, if I start my carbon molecule like this and go like this and go like this and go like this. No, let me use benzene. So for example, using benzene, we know we have something like this. We have third carbon, fourth carbon, fifth carbon, like this. Now when it gets here, you see this last carbon, this first carbon here is linked to the last carbon, right? So this molecule is actually cyclic, all right? So starting with this is cyclic. So if I draw I'm only drawing one of the canonical structures. I'm going to use just one. Now, this molecule should not be, for example, if I decide to draw this, for example, look at this. Now look at this molecule. You see that this one is bending, it's curving like this. And how many carbons does it have? This one has 1. If we start from here, 1. Or let's start from here. 1, 2, 3, 4, 5, 6. This is the 6th carbon, right? If I start from here, 1, first carbon, second, third, fourth, 5, 6. 6th carbon. If you look at it, It is fully conjugated. Why? Because it has alternating single and double bonds. Single, double, single, double, single, double, single. Here also we have double, single, double, single, double. You understand now? So there is conjugation here also. But as it is not cyclic. So this molecule is what? Not aromatic. You know why it's not aromatic now? Because it is not cyclic. Once it's not cyclic, first, it's not aromatic. Is that okay? Keep in mind that resonance is different from aromaticity. Okay, so a molecule can have resonance structures, but is not aromatic. Okay, resonance is just the spreading of pi electrons so that there is enough space for the sharing of those pi electrons. Okay, and that is why, and that resonance actually contributes to the stability of conjugated alkenes. Okay, it contributes to it. We call it resonance stability. The resonance stability is brought about by the spreading of pi electrons. There's enough space to spread about the pi electrons. So that's why conjugated alkenes will be more stable than cumulated alkenes. This is what I mean in case you don't know. So if I have this alkene, for example, now this is not, of course, when you see a linear molecule like this, an aliphatic molecule, you know that it cannot be aromatic. So, but I'm dealing with just, I want to show you what condition of resonance is. So here, this guy here has alternating single, double, single, double, single, double, single, double. So this is conjugation here. There's conjugation here. Compare this to this guy. Compare that to this guy. Now this guy maybe has double bond here and has double bond here. So looking at this is an isolated alkene. This is isolated alkene, while this one is conjugated. Okay, this is conjugated, and we also have another type. I've discussed this under alkene. You should see my video on alkene. We have this and this, for example. So of course here it will be linear. In this case it will be linear. Okay, no, let's just draw it this way so that you understand what I'm drawing. See, I put two double bonds here, and then maybe just like this. So like I was saying, this one here is called a cumulated alkene. So this one is more stable than this one and than this one. Now why is that so? Because this guy can have a resonance structure that looks like this. So you see that the double bonds are spread across all the molecule, the entire structure. So the double bond is spread across. So this is the resonance structure. So because of this reason, the double bond is not localized. It's not fixed to one position. It's delocalizable. Is that okay? It's spread across. So that's why that guy is more stable than the rest of what we have here. So basically, for cyclic, I said the first carbon must link with the last carbon. Okay, and if you look at the structure of benzene, it checks that out, right? So benzene is cyclic. How about fully planar? Fully planar geometry is basically about being sp2 hybridized. Okay, being sp2 hybridized. In this case, we are talking about the fact that, but it's not just limited to being sp2 hybridized. Okay, but just check for sp2 hybridized carbon. And what's an sp2 hybridized carbon? Any carbon that is linked with a double bond, one double bond. Any carbon that has a double bond is what is sp2 hybridized. So for example, this carbon is sp2 hybridized, this carbon is sp2 hybridized. This carbon, if it links in one bond, this one will be sp3. Is that clear? And let's check, is it fully planar? Let's see. Carbon 1, it has a double bond attached to it. Carbon 2 has a double bond attached to it. Carbon 3 has a double bond attached to it. Carbon 4 has a double bond. Carbon 5 has a double bond attached to it. Carbon 6 has a double bond. So it is fully planar. So all the carbons are what? sp2, sp2, sp2. Now you might now be thinking, how do I know one that is not sp2? Look at something that looks like this, for example. Now this one is also going to resemble benzene, but look at this. Now is this one sp2? Let's check. This carbon is sp2, of course. This one sp2, this one sp2, this one sp2. But how about this guy? There's no double bond attached here at all. So this carbon is what? sp3, because we have molecules sticking out of the board and into the board. It's not fully planar, that is, it is not trigonal planar. You know that sp2 hybridization is what gives us what? A trigonal planar shape, so that all the molecules here, they are lying on the plane of the board. Everybody is lying on the plane of the board. No one will be sticking out. But at this center here, this point will be sp3, meaning that there are some molecules that will be shooting out and into the board. Okay, so that is not fully planar. So what that means, then the third one is fully conjugated. That is the alternating single and double bond. If you look at this now, double, single, single. So also not fully conjugated. But this one is fully conjugated, alternating single and double bonds. Then Ockel's rule. Now, Ockel's rule is very important. Now, Ockel's rule is a formula, okay? One of the formulas that you learn in organic chemistry, which is 4n plus 2 is equal to the number of pi electrons that are there. Number of pi electrons. Okay, there are two ways to solving this. Now, if I want to use benzene for an example, what I want to do is this. If you want to solve for n, listen. To know if the molecule is aromatic, solve for n. If the n answer you get, I'll show you how to solve for n. So if you get n to be equal to a whole number, then the molecule is aromatic. What do you equate it to? You do 4n plus 2 is equal to the number of pi electrons. So how do you count pi electrons? The pi electrons are the ones on the double bond. So what's the second bond? This is the double bond here, right? So how many pi electrons do you count for benzene? Now let's see. 1, 2, 3, 4, 5, 6. 6 pi electrons here. So you say 4n plus 2 is equal to 6 pi electrons. By the time you solve that, this guy comes here. You have 4n equal to 6 minus 2. 4n equal to 4. Divide both sides by 4 and you have what? N equals 1. So it means that this, and 1 is a whole number. It means that our molecule is what? Aromatic, because it follows Ockel's rule. Another way to solve using Ockel's rule is this. Now listen. We can generate a set of values for our Ockel's rules, for the Ockel's rule, and we'll call it Ockel's number, so to say. So if where n equals 0, our Ockel's number will be what? Our Ockel's number will be what? N equals 0. 0 plus 2, that's 2. Where n equals 1, our Ockel's number will be 1 times 4, that's 4. 4 plus 2, 6, which was what we got for benzene, 6 pi electrons. Where n is equal to 3 to 2, 2 times 2, 4, 4 plus 2 times 4, 8, 8 plus 2, 10. So what do you notice? It's increasing by 4, 4, 4, 4, 4, 4, 4. So when n equals 3, we'll get 14. When n equals 4, we'll get 18. So this is how you do this. If your Ockel's number, if you count the number of pi electrons inside your molecule, the shape you are given, and you get any number here, then the molecule is aromatic. So for benzene, we got 6 when we counted. 1, 2, 3, 4, 5, 6. We got 6. Exactly. So that is aromatic. Now let's use naphthalene for an example. Let's use naphthalene. So look at naphthalene here. So I have something like this. And so now already you know that it is cyclic, right? So it is cyclic. So it ticks the first box. It is fully planar because we have double, single, sp2. All the carbons are sp2. This carbon is sp2, sp2 here too, because this is double bond here. sp2 here to double bond here, sp2. So all the carbons are sp2, so it's fully planar. Fully conjugated, alternating single and double bond. Single, double, double, single, double, single, or double, single, double, single. Do you see that? Right, so that's alternating single and double. How about Ockel's rule? Simply use this method now that I showed you. Just say how many pi electrons do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 pi electrons, so is here. So this guy is what? Aromatic. Exactly, it is aromatic. Now let us consider other structures. Let's consider other structures. Now look at this structure. Look at this first structure. The simplest structure like this. The simplest cyclo. Look at this guy. Has a double bond there. Now how many pi electrons does he have? 1, 2. Now first, is it cyclic? Is it cyclic? So it meets the first criteria. So let's say these are example 1, so example 1, example 2, example 3, example 4, example 5. I'm going to give us 5 molecules for example. Now for example 1, this guy, is it cyclic? Yes, it is cyclic, so it checks the first box. How many boxes does he have to check? 4 boxes. Is it cyclic? Yes. Now is it fully planar? Now what's fully planar? All carbons are sp2. sp2 here, sp2 here. How about here? This guy is sp3 here. So because it's sp3 here, it doesn't check the second box. Let's just see if it checks the fourth box. Of course, we know it's no aromatic already. But let's see where it will fall into. Will it be aromatic, non-aromatic, or anti-aromatic? Keeping in mind though that aromatic is more stable than non-aromatic, but non-aromatic is more stable than anti-aromatic. That's why I wrote them this way. Now, how about this second guy? The third box. Let's see if it ticks it. Fully conjugated. That is alternating single and double bond. Double, single, single. So it doesn't check the second box also, the third box also. Then the last box, Ockel's rule. What's the number of pi electrons? It has 2 pi electrons. So if it has 2 pi electrons, it corresponds with that, but since it doesn't meet with this criteria, we'll call it what? Non-aromatic. So it is here, non-aromatic. Exactly, our number 1 example is non-aromatic. Now, for anti-aromatic, actually, it follows this number 4n. Okay, where n is also going to be an integer, so it means that the set of values that you get for this one will be what? In the family of multiples of 4, that is 4, 8, 12, 16. I have a full video on benzene, so I'm going to link in the description. You should watch that video. Now, number 2. Let's use this example. Now let's use the same guy, but this time I am going to do something to it. I'm going to add a carbocation there. Now, so this is number 2 now. With the presence of a carbocation, something changes. Okay? Now what changes is this. This carbocation here means an empty p orbital, right? So when I was telling about fully planar shape, it is more about the empty p orbital than even the flatness of the molecule. So is it flat? That's what fully planar is talking about. So more than the flatness of the molecule, the most important thing is that there's an empty p orbital, okay? So if there's an empty p orbital, then it means that this molecule here is sp2, sp2, sp2. Is that clear? But then let's check. Is this cyclic? Yes, it is cyclic. So it ticks the first box. Is it fully planar? Yes, it is fully planar. Is it fully conjugated? So this is where we now have problem with this. Where we have alternating single and double bonds. Now, if the double bond comes here, let's see. With full conjugation, now we are dealing with the resonance hybrid that we can have. So from here, the resonance hybrid that we can have is this. That if the double bond attacks here, then we have a molecule that will look something like this. Then this guy will come here, right? By the time this one attacks this point, then we have this also. Then the carbocation will come here, and then this guy has the double bond. So in which case we are saying that we can have the double bond move around, right, fully. So since the double bond can move around fully, then it checks the third box also. It checks the third box. How about Ockel's rule? Now, Ockel's rule says that it must have 2 pi electrons, 4n plus 2, right? And in this case, it has 2 pi electrons only, 1, 2. Is that okay? So if it has just 2 pi electrons, then it checks the fourth box as well. So then this molecule is what? Aromatic. Why? Because it has a carbocation. If I put a carbanion there, look at this. Our third example. If I put a carbanion there, I'm going to use the same molecule, but this time with a carbanion here. So a carbanion simply means the presence of what? Lone pair. So there's a lone pair there. Now that lone pair, first let's check again. Is it cyclic? Yes, still cyclic. Is it fully planar? Now looking at this, you see that this is sp2, this is sp2. But of course here, this guy here has 2 more electrons more than it should have, right? 2 more electrons than it should have. Now, one thing that this electron can do is that it can participate in resonance that we just did here. It can participate in resonance. What will happen is that this double bond can be used to attack this place. If it attacks this place, what will happen is that this guy will shift. This guy will shift. When he shifts, this guy will come and form bond here. So the resonance hybrid will look something like this. The new position that was attacked will have a double bond. And this guy will shift on this guy. So when he shifts, then our lone pair will stay here. Is that clear? Then what will happen again is that this lone pair can come back to attack this place. If he attacks this place, then this guy will shift on this guy. If he shifts on this guy, what happens? This guy has attacked this place, then our lone pair stays here. Do you see that now? So we can have 3 resonance structures for this guy too. Now, with these resonance structures, does it now follow Huckel's rule? Huckel's rule says 4n plus 2. Now, 4n plus 2. How many electrons do we have here? We have 1, 2, 3, 4. Now we have 4 electrons there. Now is this guy, does he conform with, does he have any of these numbers? Is he one of the Huckel's numbers? No. So 4n plus 2 is not here. And by the time you calculate that 1, 2, 3, 4, that's 4 electrons. And there's no 4 electrons here. But does it conform with anti-aromaticity? Yes. There's 4 here. So our molecule is in fact anti-aromatic. It only checks 3 boxes. Is that okay? Doesn't check the last one. Is that clear? So that is that about that. How about number 4? Let's draw another molecule. Number 4. What if I put this? A molecule that looks like this. Okay, we might do up to 6 or 7 examples. Let's see. Oh, sorry. Our number 2 was, we checked aromatic box, so it should be in number 2. Number 3, checked anti-aromatic box, so it should be in number 3. Then the next one is number 4 now. So if I put a molecule like this, for example, all right, now let's see, this one already is cyclic, so it checks the first box. Is it fully planar? That is, are they all sp2? Yes. This carbon here will be sp2, 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 sp2. Is it fully conjugated? Yes. Single, double, single. Double, single, double, single. So it checks the second and the third box. How about the last box? Now, where does it conform with? Now, how many pi electrons do we have? 1, 2, 3, 4. 4 pi electrons. So we have 4 pi electrons. Which number does it conform with? Is it anti-aromatic or aromatic? There is no 4 here. 4 appears here. So it is rather anti-aromatic, not aromatic. It doesn't check the last box. So let's draw another molecule for an example. What if I have this molecule, for example? I don't know which one to draw now. So look at this molecule, and then we have this. Now looking at what you have here, you already know that. So let's see, is this guy cyclic? Yes, it is cyclic. Fully planar, sp2, 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 but here is sp3, so it doesn't check the box. How about fully conjugated? Double, single, double, single, single. Not fully conjugated again. How about Huckel's rule? 1, 2, 3, 4. 4 electrons. So if there are 4 pi electrons, then it is anti-aromatic. Is it clear? It is anti-aromatic. Oh, sorry. For anti-aromaticity also, it must be fully conjugated. So this guy is non-aromatic. The conditions for anti-aromaticity is cyclic also, fully planar, and fully conjugated. But the number is this guy that changes. Is that clear? So you see the guys we did these 2 guys. They go with these 2. They have these 2 properties, but not the last. Okay. So that guy here is supposed to be non-aromatic. Then number 6. What if I had a lone pair here, for example? Or let's add a carbocation here first. If I add a carbocation here, what will happen? Now, what will happen is that this guy can be delocalized, but of course, you can already see that it's still 2 pi electrons that we have. So this guy is not still going to be aromatic. Is that okay? It's not going to be aromatic because we have 4 pi electrons. So, but will it be anti-aromatic? Yes, it will be anti-aromatic. to be anti-aromatic because it will conform with those three, but not with the last one. What if it were a carbanion I had here? What if it were a carbanion? That is the presence of a lone pair. Now, if there is a lone pair, then it means that this lone pair is going to contribute to the resonance structure. It can attack here, then you have this thing will shift. If it attacks here, what will happen is that we'll have a molecule, a structure that looks like this. This double bond has shifted here, and with that, this guy will also collapse here. So if this guy collapses here, we have a double bond here. Then this one will come here. So if this one comes here, then we'll have our lone pair stays here. So this is a resonance structure. The next resonance structure will be where this guy is attacking this place, and like that, until you rotate it over, I think, 5 places like that. So it's going to have 5 resonance structure. Now, what will happen with this? Is this guy going to be planar? Yes, planar. Is it going to be cyclic? Yes, cyclic. Is it going to be fully conjugated? Yes. But will it follow Ockel's rule? Let's see. How many electrons do we have? 1, 2, 3, 4, 5, 6. 6 pi electrons. So with the presence of a lone pair, this guy, okay, our number 6 was a carbanion. With the presence of a lone pair, this guy becomes aromatic. Is that okay? With the presence of a lone pair. So that is it. That will be it on aromaticity. Do want to subscribe to the channel and see the video in the description where I fully talked about benzene and aromatic compounds and how to name. I did many things concerning aromatic hydrocarbons in that video. Do well to watch it and share this video with your friends. God bless you as you subscribe to the channel.